group for today. I want to welcome everyone on behalf of the Phys division of the ACS, as well as the other co-hosts, Rodrigo Noriega, Carlos Pais, and QC. Excuse me, to our Phys division. Now it's bi-monthly or semi-monthly webinars. And today we're continuing on with honoring our 2021 division awardees by welcoming Nancy Makri from the University of Illinois at Urbana-Champaign. Nancy is the recipient of the 2021 ACS Phys Award in Theoretical Chemistry. And I apologize, something went down wrong. Nancy received her bachelor's degree from the University of Athens and her PhD from the University of California at Berkeley. She then went on to Harvard as a junior fellow and joined the faculty at the University of Illinois in 1992, where she's been on the faculty ever since, rising through the ranks and getting a plethora of awards. I'm not going to go through all of them. Obviously, the most important one is the ACS Phys Award in Theoretical Chemistry. But in addition to that, she received the Agnes Faye Morgan Research Award. She's received Beckman Award, and even more recently than the ACS Phys Award, she was elected. It was announced about a month ago that she was elected to the American Academy of Arts and Sciences. So please join me in welcoming Nancy, and I look forward to your talk today on real-time path integral methods for electron vibration dynamics of large systems. And thank you for joining us today. And I will stop sharing screen.
Just one further note, as usual, as the presentation goes on, attendees can type their questions in the chat function of Zoom or in the comments for the YouTube stream. And we will curate those questions and ask them at the end in a moderated session. Thank you.
Thank you, Rodrigo.
All right. Thank you so much. And I lost my controls now, though. I hope I won't need them. Let me get them back. Well, okay. Well, maybe not. I'll go without them. All right. Thank you so much.
And you need to share screen too.
Oh, so okay, that's fine. So back to sharing and everything, back to controls. There we go. Okay.
Great.
There we go. Okay, thank you so much for the invitation, and it's a pleasure for me to be here and I have a chance to tell you about our adventures. You know, during COVID time, everyone needs something, some excitement, right? So I'm so fortunate. The research has been so exciting and so much fun. So we are a theory group, and we develop methods and theoretical approaches for following the dynamics of large systems, condensed phase systems, and quantum dynamics in particular. And today I'm going to tell you about some of the methods we've developed over the years. And specifically, I'm going to focus more on electron vibration dynamics. So what are we trying to do? We have a Hamiltonian for some large system that describes a process of interest, say some electron transfer or some energy transfer. And there are many states involved and many degrees of freedom, and possibly a condensed phase environment, a solvent or biological molecule or things like that. And we would like to study a quantum mechanical process. So we would like to be able to account for quantum effects accurately. But we also need to take into account all these degrees of freedom of the environment, a large environment. So typically when you have situations like this, you are not interested in tracking every coordinate of every molecule in the solvent and everything like that. So what you focus on is a property of the, what you call the system, which is the subsystem that you tag. Could be the electron transfer pair, could be a proton coordinate, for instance, or it could be the energy of the electronic energy of a system, for instance. So this is a way to describe this. one uses a concept of the reduced density matrix, which is the density matrix of the whole system plus environment, everything here, given by this, traced with respect to degrees of freedom of the environment. So if, for instance, if I'm looking at the electron transfer in solution, I'm going to have an initial density operator, which is an operator in the space of the electron transfer pair and all the solvent coordinates, everything else. And I'm going to take this and propagate it forward and backward in time. And that gives me rho of t. And then I trace with respect to all the degrees of freedom of the solvent or biological environment, and I get a small density matrix. That's a matrix for the subsystem of interest, say electron transfer pair. If that's a two-state system, I'm going to have a small reduced density matrix here. All right, so that's what we are after typically, and we can adjust this to whatever we need. We can also, in a similar way, we can also calculate time correlation functions that are very important and capture very interesting information. So that's what we're after. Now, how can we do this? Of course, you could say one way to do it would be to solve the time-dependent Schrödinger equation here. Here it is. Now, if I do this, and if I want to do this accurately without major assumptions or without compromising in the dynamics, I would need to store the wave function. And that's the wave function of everything. That's the wave function in all the coordinates, the electron transfer pair and all the solvent coordinates, thousands of coordinates. And you all know how quantum mechanics is infamous for its exponential scaling. So the storage of wave function, the size of the object you need to store here to not have the wave function grows exponentially with the number of degrees of freedom. So that's out of the question. If you have a condensed phase process, you cannot store the wave function of 1,000 water molecules. It's not possible in practice. So what can you do? Of course, the standard approach, a very pragmatic approach, is to introduce approximations. You can do all kinds of things, all kinds of ideas here in approximations, and many approximations are, very efficient and very insightful, and you can get very far with approximations, but very often also approximations break down. And also very often you don't know when an approximation is correct for a particular very complicated process. An approximation might work very well in one case, one might not work in another case. So what we try to do is we try to develop approaches where we don't have to introduce drastic approximations, or ideally we can solve the quantum dynamics exactly without any assumptions, any dynamical assumptions at least. Can we do this? Well, if we want to do this, then it's clear that you can't really just go by solving the Schrödinger equation here. You're going to have, it's too much storage. You can't really proceed if you have to store the wave function. So how can we do this? We've been, our work has been based mostly on a different approach of different formulation of time-dependent quantum mechanics. That's due to Feynman. It's called the path integral formulation of quantum mechanics. And some of you, I'm sure, have heard about it, but many others probably don't know much about it. So this is, actually, it's my favorite formulation of quantum mechanics, even though when I teach graduate quantum mechanics, I follow the traditional approach because there's some very important concepts there, important background and tools. But this is really very intuitive. That's what I like about it. What is the path integral? It's basically a generalization of the double slit experiment. And I'm sure all of you have seen the double slit experiment. It's usually discussed on first day of quantum mechanics, kind of to motivate the particle wave duality. And the idea is once you give up the particle description of matter and you go to a wave description, then you can explain the interference pattern. And that the explanation is very straightforward now because we understand that waves interfere, unlike classical particles. Waves have the ability to interfere. So what we say here is if there is a particle that's described as a wave, and it can go through one of these two slits, it has an amplitude for hitting this point on the detector along this path, and a different amplitude of going through the other path. And the two amplitudes oscillate. They're oscillatory functions, like ordinary standard wave mechanics that probably some of you have seen in high school. So you add the two amplitudes, and that gives you a total amplitude of the wave. And then you say if this is wave mechanics, the intensity of the wave, for instance, is the square of the amplitude. If this is quantum mechanics, you take the absolute square because we go to complex numbers, complex phases, complex amplitudes, and the absolute square of the sum of the amplitude would give me, in quantum mechanics, the probability of getting from here to there. So the probability is formulated as the square of an amplitude, and when I square a sum, I get cross terms. And the cross terms, as I'm sure you remember from a double slit experiment, it's the cross terms that give you all the quantum interference. They give you interference fringes here. And that's how you see that quantum mechanics, through this particle wave duality and through this concept of a sum of paths, quantum mechanics gives us interference patterns, gives rise to interference patterns. So this is all very, I think, simple and intuitive. And it's basically, this is what a path integral is. So the path integral is exactly this, extended, generalized, to have many slits and many partitions here, many walls. So imagine that you had many walls and each of the walls has many slits, right? And you, of course, you'd have many, many more paths. With the postulate is that the total amplitude is the sum of amplitudes along all these paths. And then all we need is a prescription for what this amplitude is, the amplitude along a path. And according to Feynman, the prescription is, the postulate is that the amplitude is the exponential of I over h bar times a classical quantity. That's the action integral here, the classical action, which is the integral of kinetic minus potential energy, in most cases, along a path. Path is like a trajectory. So these are classical concepts, but the paths are not classical. The paths are just any line I can draw as a path. So this is a prescription, the formulation, and this is an exact formulation of quantum mechanics. So again, it's so simple, right? So elegant. And what is very nice about this is that if you take this postulate, you can derive from this the time-dependent Schrödinger equation. I find this very satisfactory, very pleasing, because I find this much more intuitive and easy to believe, right? Much more than a partial differential equation in space and time. So great physical insights from this. By the way, this gives us a lot of physical insights. For instance, if you ever wonder how quantum mechanics goes over to classical mechanics, the semi-classical limit or classical limit of quantum mechanics comes out immediately here from this prescription. All you have to do is notice that there's a lot of interference in this sum. In fact, this is the essence of quantum mechanics. Is in this sum, there's a tremendous interference. And out of this interference, the cancellation of paths in the classical limit, what we get is that only the paths that give rise to a stationary action does not vary very much. Only those these dominate and these survive in the classical limit. And once you understand this, it's called a stationary phase approximation. Once you understand this, you see that the condition for classical paths to dominate is the condition that the first variation of the action should be equal to 0, which is Hamilton's principle of least action. So immediately here, in a minute from this, you can get the can derive classical trajectories out of this in the classical limit. And I'm not going to say much more about this, but it's a great starting point for a lot of treatments, a lot of different treatments in physics. And all areas of physics have used the path integral very, very much. And it is also it also gives a great connection with quantum statistical mechanics, finite temperature properties, and I'm sure some of you have seen this. All it takes to go from quantum dynamics to quantum statistical mechanics is to change the I here to a negative sign. For the way this happens is that you turn the time to imaginary time, and the reason is that the operator responsible for quantum dynamics, which is the time evolution operator, has the same structure as the Boltzmann operator. The time evolution operator has negative IT over h bar multiplying the Hamiltonian. The Boltzmann operator has beta 1 over kt multiplying the Hamiltonian. So it's the same structure exactly. So you can get all of quantum statistical mechanics from this once you change the time to imaginary. And that leads to very practical methods for getting quantum mechanical properties of systems in thermal equilibrium, in the thermal ensemble. For instance, you can do numerically exact simulations of superfluid helium-4 this way and see quantum mechanical effects in helium-4. So all kinds of beautiful things here about this formulation. All right, so let me now get a little more specific about this. So let's say that, let me apply this idea to a system described by a coordinate x, and this could be a collection of coordinates. I'm just drawing it here, just giving, drawing cartoon presentation of these paths, and here's the time axis. So if I want to evaluate the full path integral, I need to calculate all the paths. Let's say I start this point here, this x at time 0, and I want to go to this x at time t. So I need to consider all the paths that connect the initial and final point, and of course there's an infinity of them in reality. But when we calculate things on computers, we always discretize everything. To be able to put this on a computer, I need to discretize the spatial coordinate x, and I'm going to set up a lattice here along x, a grid, and I'm also going to discretize time into a grid of time points separated by my time step. And now I have a lattice of x versus t, so the paths live on this lattice. So how many paths do I get? Well, if I start at this point, that's a fixed point, after one time step, I've got n different options for connecting from an initial point to first point, and little n here is going to be the number of grid points I have along my spatial coordinate. So n possibilities after one time step. After a second time step, from each of these grid points, I also have n choices. So after 2 time steps, I've got n squared paths. After 3 time steps, I've got n cubed paths, and it keeps going like this. And you see that the number of paths grows by n every time I add the time step. So if I want to go to this number of time steps, t over delta t is the number of time steps, then this is the total number of paths that I get. And now you realize that this, what appears very nice and simple and very elegant, it is actually very elegant, is not a piece of cake to evaluate. In fact, we're going to get astronomical numbers of paths here if we want to describe anything of real interest. So even if I have a two-state system, electron transfer pair, for instance, nothing else, just a two-state system, and I need to go to 100 time steps to calculate the dynamics, I'm going to have 2 to the 100 power paths. Now, by the way, I should say that if you start working with path integrals, very soon you realize that what you tell beginning chemistry students, you tell students Avogadro's number is very large, right? Well, you just have to think Avogadro's number is nothing here, because we get those huge numbers of paths here that Avogadro's number looks like. It's not that big, right? So very quickly, I'm going to get here numbers that are exponents that are so large that they can't even think about this. So how can you evaluate this sum over paths? Well, I mentioned a minute ago that this formulation also is applicable to quantum statistical mechanics, and you can sample thermal properties, canonical ensemble properties, and that is actually very efficient. That's done very efficiently by Monte Carlo method, stochastic sampling, or sometimes people use molecular dynamics instead of Monte Carlo. So these methods are actually very, very efficient. You can sample the space, but only if you have the Boltzmann operator, if you're looking at thermal properties. The reason for that is that when you have the Boltzmann operator, your integrand, imagine this huge space of those amplitudes, all those paths, the amplitudes then would be real numbers if you have the Boltzmann operator. And the vast majority of those configurations don't contribute because there's an exponential factor with a negative sign in front, and the weight would be something like the energy. And you know that the space is very sparse, very empty. So there are very select configurations that contribute, and Monte Carlo is fantastic for finding those configurations. So that's actually a very different problem. In real-time dynamics, however, what we have is a situation where all those amplitudes come in with the same weight. The weight is a complex exponential. It's a pure phase, in other words. And when I take the modular square of a phase, I get 1. So all the paths in real-time dynamics contribute the same weight, with the same weight, and that might sound, again, crazy, very counterintuitive. Imagine if you're an electron and you want to go an angstrom away. Well, the probability of going straight line an angstrom away is going to be the same as the probability of going to the moon back, right? It's both paths come in with the same probability. So again, sounds crazy. It's crazy quantum mechanics, right? That's the way it is. And again, the reason that, of course, in practice, the paths that go to the moon and come back or to another galaxy, the reason that these don't contribute as much is because of cancellation. It's destructive interference that they just cancel out. When you sum over all of them, even though they're all important, they cancel out one another. And you can see this cancellation in this plot here, this figure, where I'm plotting the real part of that amplitude as a function of one spatial coordinate. And look at what it looks like. It oscillates from +1 to -1, like very, very, very dense oscillations here. It oscillates very, very rapidly. Most places, and now you can see how when I sum over all these contributions or integrate this function, most regions where I have dense oscillations are going to cancel out. Positive with negative cancels out almost precisely, and most of the space doesn't contribute, doesn't give me much, except for these regions like here, this one and that one here, where you see the positive area is not the same as the negative area, and these are again the stationary phase regions. So the problem, however, now is that the entire space of integration, the entire space I need to sample and include and sum over is important. I cannot just ignore, I cannot just drop the majority of paths. I've got to account for all of them, and I've got far too many of them. And Monte Carlo methods here cannot help me. If the entire space is filled, and if the amplitude is highly oscillatory, you have to integrate a highly oscillatory function. Stochastic methods cannot do this. You need to very delicately account for this cancellation of positive and negative regions. So we've got a real problem here. We've got far too many paths to enumerate and sum by quadrature. At the same time, Monte Carlo stochastic sampling methods cannot work because of a problem. This is called the sign problem, by the way. It's very similar to a problem that occurs even in the thermal ensemble, when you have particle exchange of identical fermions, and then you get negative signs there as well. So this is called the sign problem. I would say that the sign problem of quantum dynamics is far worse than the sign problem of fermions, actually. So we've got a real problem here. So how can we do this? Is there anything we can do to make some progress? Well, the philosophy, the idea we've been pursuing, we've been based our thinking over many years is the following. Can I disentangle, can I study the dynamics, understand the physics, and by doing this, can I disentangle this enormous sum and break it up into pieces that I can handle on a computer efficiently without losing any accuracy? That's the name of the game. Without doing, I don't want to do this approximately, I want to do this exactly. Can I do this? So let me give you a better idea, an analogy here to show you what I mean by saying, can I disentangle this sum? So here's my very simple third grade example. Let's say I'm given this multiplication. I'm told I need to multiply these numbers. So you look at it, and at first glance, you say, I've got to do 3 multiplications, long multiplications, right? That takes some work. But then you look at it a little more, and you realize that there is a 25 here, and it's squared, so there are 2 25s in this factor, and there are 2 4s in the other factors. And now, if I combine the 25 with the 4, I get 100. So there are 2 hundreds here. And you see then what I'm left with is single-digit multiplication. I can do this in my head, and then all I need to do is add 4 zeros. So I've done it without doing any long multiplications. Obviously, this is exact. It's an exact decomposition. All I did is rearrange my factors, and I was able to do it without doing any real work. Now, you could say, of course, I got a little bit lucky. Definitely, I got lucky. But perhaps for many systems, we can get lucky. We can identify structures that allow us to disentangle this path integral and turn it into something we can handle. So that's the idea. So over the years, we've been able to do this in a few general classes of problems, general classes of systems, of Hamiltonians that are important, have in a lot of different problems. And we have developed exact methods, numerically exact methods for some of these. And I would like to tell you a little bit about all three of these, actually. I'm going to focus I'm going to focus on all three a little bit, right? And probably more on the last one, which is what we're doing right now. So let me tell you about this. So I'm going to now specialize to, soon I'm going to specialize to certain types of Hamiltonians. But before I do that, let's look a little bit at the structure of our problem. So here is a Hamiltonian, a general Hamiltonian. This could be anything, really, in a general environment. And I'm going to now tag a particular degree of freedom or a few degrees of freedom as my system. There is nothing special about this other than this is what I'm interested in observing. In other words, I want properties that pertain to this degree of freedom S. Again, this could be an electron transfer pair, could be a proton coordinate, something like this, right? That's what I'm tagging, the tagged particles. And the rest is going to be what I call the environment, right? So the environment is going to be all the coordinates, all the other degrees of freedom I have in my system could be very, very complex. So at this point, no assumptions here about this. So, and I call all these degrees of freedom Q of the environment, right? So let's start by writing down the reduced density matrix of a system that we want to obtain. So here it is. It's going to be a matrix in the coordinate of the particle at the time, the final time. I'm going to use here the subscript. I'm going to alternate between continuous notation and discrete notation. And here I'm using n, the index n, to indicate the last time point. So I'm going to take, very soon I'm going to take the time coordinate and I'm going to divide this into time steps as I showed in the picture. And n is going to be a total number of time steps. So if I want to go to time t, I'm going to take t divided by n, and that gives me my time step delta t. So here's the reduced density matrix, and I also label this, by the way, by the initial by coordinate that could label my initial density matrix here. Okay, I'll show you in a second, actually. So what I do here is I want to obtain the path integral representation of this object. What I do is I go to these time evolution operators. There are two of them, and I split the time into steps. And then what I get, this exponential becomes a product of exponentials that involve delta t. So the exponential of a sum is a product of exponentials. So each of these turns into these short time evolution operators. And I'm trying to give a little bit of background here. Okay, I'm not going to give, this is not a full tutorial because we'll go far beyond the hour. And all right, so I get a product of all these exponentials, and then I go and insert complete sets of position states, resolution of identity in the space of a system. So I get this sum over all these auxiliary variables here that are the coordinates that I was showing that cartoon of the paths, that the realizations of the path. They're coordinates and to sum over all the paths. So these coordinates are going to be called S1, S2, up to Sn minus 1 to get me to the final point Sn. And there's also a superscript here, which is a plus or a minus, depending on whether those coordinates that I'm using, those auxiliary variables I'm using, are variables to discretize the forward time evolution operator or the backward, the reverse time evolution operator, that one. So that's what the plus and minus means. So I'm summing over all the paths of everything, actually, here. If I want to do this, and turn this into propagators, I'm going to sum over all the paths of the system and all the paths of the environment, everything. So imagine that's also the same here, discretization of the Q variables. That's a full path integral. And what do I get inside? So all these short time propagators, if you work out the expressions, they give you phases, like the amplitude of the formulation is a phase of a formulation again. You get all these phases here, which I've partitioned into the phase that comes only from the system, and then the phase that comes from the system and its interaction with the environment. So this depends only on the S variables. The other one depends on the S and the Q variables together. And here's my initial density matrix of the system and the environment, everything. And here, so I get an exponential that corresponds to this evolution operator, another exponential corresponds to that evolution operator. So it looks like a big mess, right? But notice it's all phases. It's a sum of amplitudes. So everything here other than the initial density matrix is a phase. How can I do the sum? Of course, that's horrendous. Right? I can't really do this. So, but imagine now formally that I go and just formally and do the sum over the variables that correspond to the environment. So everything that has Q, I'm going to sum over all the yellow parts here. And what will I get? If you have a function of two variables, let's say x and y, and integrate over x, what do you get? You get a function of y. So when I sum over all the q's here, I'm going to end up with a function that depends on the s variables. Here it is. I call it f. So this f depends on all the system variables, all of them, and this is called the influence functional. That's what the influence functional is. Actually, not it's not so bad. It's pretty straightforward to see this. Now, in general, I don't know this. I can't calculate this. Maybe I can in some cases, right? That's what we're going to try to do. But in general, I don't know this. So you could think that first thought here is, can I obtain this influence functional? And second is, once I obtain the influence functional, can I evaluate the rest here of the sum? Notice now that by doing this, I am going to a subspace. So when I started writing this whole path integral, I was in a space of all the variables. And that was something I could not really handle. It's a huge sum. But what I have here is a sum that involves only the system variables. So that's great progress, right? If I know this, great progress. I have a reduced dimensional space here. At the same time, however, this influence functional really complicates things. Because if I didn't have this, the path integral description of the system alone would be equivalent to the time-dependent Schrödinger equation for the system alone. And if I had the time-dependent Schrödinger equation for the system, a small system like a two-state system or a one-coordinate problem, I would be crazy to try to evaluate by the path integral. I wouldn't do that. I would just solve the time-dependent Schrödinger equation, which I can do step by step because it is a simple differential equation, first order in time, and I can go from one step to the next, and from that step to the next, and so I can do this iteratively in time, and I can very easily get the exact answer. So when we have a situation like this, we call it Markovian dynamics. What happens at time t depends only on what you had at the previous t, or the previous time step, or another way to say it is, if I'm at time t and I know my wave function, I can evaluate the Hamiltonian on the wave function, and from this, I get a time derivative of the wave function, so I can propagate to the next time step, just like I can do with classical trajectories by propagating Newton's equations. So that's simple. The problem now is that this influence functional, when I have the influence functional coming from a large environment, any environment, this introduces interactions that are non-local in time. This means that all these variables are coupled now to each other. So I can no longer take this and map it on a simple first order differential equation in time. In fact, this destroys the Markovian character of dynamics, and we get memory effects and correlations. And I'll show you what this actually means here once I specialize to this first case here. So the first case is what I call system bath dynamics, what is known as system bath dynamics. I am going to assume that my Hamiltonian is composed of a small system that is coupled to a bath of harmonic oscillators. Now, these harmonic oscillators could be a lot of different things. For instance, they could be the normal mode coordinates, the normal mode vibrations of a molecule, right? Immediately get a harmonic bath. They could be the phonons of a solid, of a lattice. You get the phonons are the normal mode of a lattice. So phonon coordinates, normal modes. There could be a lot of other things as well. There could be a theorist's description, simple description of a condensed phase environment. If you want to see what are the generic effects that the condensed phase environment introduces to the dynamics of a system, you work with system bath Hamiltonian, because this harmonic bath can capture all of these condensed phase effects. And what I have in mind here are effects like dephasing, decoherence, coherence as well, quenching of coherences, quenching of oscillatory structures, all kinds of quantum effects, right? So you could be just using a system bath prescription. Also, I wanted to mention that system bath Hamiltonians are important for many other processes as well, even though you may not be able to identify a harmonic environment when you look carefully. So for instance, if you have an electron transfer process in solution, a solvent can never be described by a harmonic bath, at least not, for most standard processes, because if you were to, I should qualify this, at the microscopic level, you cannot really define harmonic bath coordinates by doing a normal mode expansion. That's what I meant to say about a particular configuration of a solvent, because the solvent, by definition, the atoms execute large amplitude motion, right? The molecules move around, they diffuse, and if you were to freeze the solvent and do a normal mode expansion, you couldn't go too far. If you wanted to go farther, you would have to take another expansion point. So you can't really identify microscopic normal mode coordinates for a solvent, yet very often you can use system bath descriptions for a process in solution if it's an electron transfer process, and that is the idea underlying the Marcus theory of electron transfer, where the solvent is described by harmonic oscillators. Of course, back when Rudy Marcus developed all this, I'm not sure any of this was known, but of course, back then, all a theorist could do was to use harmonic oscillators, right? You couldn't do much more. So it turns out that this harmonic description is also relevant there because of interesting reasons, deep reasons, because of the central limit theorem, basically, that gives rise to Gaussian response. So I'm not going to say much more. Actually, it looks like, oops, I need to speed up a little bit here. All right, so for a system coupled to a bath, the harmonic bath, we have a Hamiltonian like this. The harmonic oscillator coordinates here and here, the coupling terms to the system. And incidentally, if you take this Hamiltonian, you can work with this, and you can show that within classical mechanics, this system bath Hamiltonian gives rise to the generalized Langevin equation. And you can derive actually a GLE from this, and you can see what the friction term is, where it comes from, and so on. So it gives rise to this to dissipative effects. You can see here coming from the friction terms. And it's a great model, again, for classical mechanics as well. So for quantum mechanics, in our case, what we can do is go and evaluate the influence functional exactly. Feynman and Vernon did this back a long time ago. And we can do this exactly because you can do a lot of things with harmonic oscillators. They come in as Gaussian functions, in the quadratic functions in the exponent, and can evaluate exactly. And you find this form. You find that the influence functional is given by the exponential of a double sum, where inside you get those system coordinates that all couple together, and the function that couples together the system variables at the time t prime to the variables at the time t double prime. The function that couples these is this function here, alpha, which is the time correlation function, the force correlation function, in fact, of the bath of the environment. So if you know this, you know the influence functional, but notice that all the variables are now coupled. So how can we evaluate this? The problem here is that, again, because all variables are coupled, when I evaluate the path integral, I would need to evaluate the whole sum globally for all the variables. But if I want to go to 100 time steps, which is actually not that long, I would need, for a two-state system, to the 100 paths. I cannot really afford this. Exponential scaling with time. So back long time ago, back in the 90s, early to mid 90s, when I was starting on the faculty at the U of I, we realized that this can be done, actually, this can be decomposed. There's an exact decomposition of the path integral. And that's because those couplings between path integral variables don't continue forever. They have a finite span. You can see here's my time lattice. And if the span is equal to 3 time steps, that means I can go from this point to this point, or that point, or that point. That's it. But if the span is 3 time steps and not 4, it means if I look at the coupling at 4 time steps, that is very small, I can ignore it, right? If that's the case, then I only need to worry about these interactions. And you see now the structure of this. It allows me to devise a tensor decomposition. So what I need to do is set up paths that span this length here, which we call the memory length or correlation length, correlation in time. I'll call it memory length actually, usually. So I need to set up I need to store the variables only along the memory length, and then I can take the paths that span this memory length. I can form an array of the paths, so I can see it as a tensor of 3 indices here. And I can connect this to the next one by putting in the right couplings. So you see I can go from the 3 here, assuming here for the picture 3 time steps of memory, I can go from the green points to the yellow points to the pink points, and I can continue like this. And now by doing this, I have turned the exponential scaling with time to linear scaling because I'm doing this iteratively. So this method became known as QAPI, iterative QAPI. And what you see where I'm doing is I need to store a tensor of these of the system coordinates that span all the time steps from the memory and do tensor multiplications, and I propagate in time. And for small systems, you can do this very efficiently. You can study a lot of processes, and there have been a lot of applications on this. All kinds of things: electron transfer, energy transfer, reaction rates, proton transfer, all kinds of things, spectra, all kinds of things have been done this way. Okay, so that's how this goes, and we can do this for harmonic environments described by arbitrary spectral densities. You can just, if you are able to get the spectral density of the environment, it could be something structured like this. You can apply QAPI, and this is really, there's no restriction. Now, the number of paths I get within memory could actually be large because I get exponential scaling formally within the memory length, right? So if I have a 2-state system and take forward and backward coordinates, for 3 steps, I would have 2 square, that's forward and backward coordinates, as the size of my reduced density matrix. So 4 to the 3rd power paths. And if I have 10 steps in memory, I get 4 to the 10th paths, and I can handle this. But to go far beyond that, we need to use other tricks. And there have been a lot of tricks. We developed some of these tricks, like filtering approaches. The blip decomposition is something we developed actually more recently. And many other people have applied SVD ideas, lots of different ideas here. And by using these kinds of tricks, basically, you throw out paths that have negligible contribution even within memory. And you can now go to much longer times, and you can do calculations with much more demanding calculations. So even back in 1995, we're able to do 3-state calculations of electron transfer in photosynthetic reaction centers, where we had to go to 35 time steps of memory to converge, right? So it's not like it's very restricted, but you have to do a lot more work if you have to cover long memory, and especially if you have a large system that consists of many states. So I want to show you some recent progress here, and I'll discuss this very quickly. So I used to think that this is all one could do because there is no free lunch, right? So this means that you would need to cover everything exactly within the memory length. That means you really have to account for everything within memory, and you need to build those tensors and you need to store the tensors, and there is no way around this. But it turns out that that's not the case, and you can further decompose this tensor multiplication scheme into small matrix multiplications. So what I have now, and this was all done last year, actually, very, very recent. What I have now is a similar decomposition. It's still iterative in time, but what I now have is small matrices of the size of the system. So for a 2-state system, these are 4 by 4 matrices. Nothing, no storage at all. For a 10-state system, these are 100 by 100 matrices. Oh yeah, no problem at all, right? We can do these kinds of things. So we can now go to much larger systems and much longer memory with this, without worrying about storage at all. So we call this small matrix path integral, a small matrix decomposition, or SMAT-PI. And it really has given us new capabilities here. We can do a lot of things that we could not do before. And here's some just illustrations here. We can do processes with very long memory. We're going to 100 or 200 time steps of memory, actually, for a 2-state system. We can do 10-state systems, 16-state systems. We can go, we can do much, much more with this, right? Right away, without any fancy tricks. So, okay. So, and I'm probably going to skip this. As we develop new ideas and new methods, we always go and study some interesting physical and chemical processes. So sometimes we take model Hamiltonians and we look for effects for interesting phenomena. And sometimes we look at we use actual molecular parameters to investigate specific effects in molecules. So one of these calculations I'll just describe very quickly that Sambarta did, and Sambarta is now my postdoc at Princeton, was to investigate the purity of the reduced density matrix in systems, and that's because purity has been tied to decoherence and to entanglement and all kinds of things. So it's a very interesting story here, but I don't have time to tell you, but all I may perhaps say is that in some regimes of high temperature and strong dissipation, purity decays in a similar way with populations as the reduced density matrix decoheres. But if you're at low temperature and weak or intermediate coupling, that's not the case. And even though the system loses coherence eventually, purity actually recovers and goes back. And there's very interesting physics here. So, but and this is not just a fictitious scenario of a theorist. This is the case with a lot of things, like the chlorophyll dimer here. This is the purity of the excitonic energy. I'm going to talk more about this in a few minutes. And I just wanted to show here that it's a very interesting physics, actually. All right, let me move on. So the second method I would like to, the second situation where we've been able to do decomposition is the quantum classical dynamics. If I have a system coupled to a solvent or biological environment, and here I'm not going to assume this is a harmonic bath at all. It's going to be a very complex environment characterized by many body and harmonic interactions. Everything is there. So quantum classical methods, I'm not going to say much about them. Actually, that's a very pragmatic approach when you have a complex environment. You can't really do the full quantum mechanics, but in quantum classical methods that are based on wave functions, you have to make some major assumptions, and these are related to Reinfeldt's dilemma here. And I think I'm going to skip a lot of these discussions here because I think time is going very quickly here. So, So it is very hard to avoid these inconsistencies when you use wave functions. And the reason you run into inconsistencies is because classical mechanics is local, while quantum mechanics is delocalized. The classical mechanics, the classical trajectory wants to know a force. How do you evaluate the component of the force from the quantum particle? That's described by a wave function. It's delocalized. And all you can do is take the average. That's mean field theory, basically. And then if you don't want to use mean field theory, which gives you physical results, you have to go and develop and make other assumptions and develop other ideas, right? But now you realize that if I stick to the path integral formulation, the non-locality issue goes away because quantum mechanics is local, one path at a time. So I can immediately couple a quantum path to a classical path without making any assumptions, any mean field assumptions or anything. And this gives rise to the quantum classical path integral, which is fully derivable. It is the stationary phase limit or the semi-classical limit of the full path integral for the system plus environment, stationary phase with respect to the environment. So out of this, we get classical trajectories for the solvent, and we get an interesting structure where the classical degrees of freedom provide phases that modify the amplitude of the quantum paths of the system, and the quantum paths of the system drive the trajectories of the solvent. So here it is, and we get the structure. We have a large phase integral here that over initial coordinates of the environment, and also a sum with respect to states of the system, which is here. And everything in this formulation comes from all the decoherence, all the interactions come from these phases. There is nothing else. So you look at it at a glance and you say, how can I evaluate this? And the problem we get, of course, is we get again this exponential proliferation of the paths of the system. Can we disentangle this? And it turns out that we're able to disentangle this by understanding the physics of decoherence. And I'll make a long story short here, a very interesting story. But it turns out that the coherence of a quantum process has two contributions. In fact, it resembles effects that we understand from absorption and emission of light. So one of these contributions that we call the classical contribution, the coherence, is analogous to what you get when you treat the quantum mechanical radiation field as a time-dependent oscillating dipole. And that classical decoherence then is associated with, or the mechanism of classical decoherence is exchange of energy between the system and the environment by means of stimulated absorption and emission of phonons, now in this case of energy, quanta. In the case of, and the other contribution to the coherence is by a quantum mechanism, which is related to spontaneous emission of phonons or spontaneous emission of energy between system and environment. I don't have time to tell you in detail, but it turns out that this is easy to account for, as you might imagine. And we do this, we take advantage of this to get a much better starting point. This is much harder to account for, but by taking this and some other ideas into account, we are able to turn this into a very pragmatic scheme. And what you see here is an application of this to electron transfer in the ferrous and ferrocenium pair in solution in liquid hexane. Here the solvent is described in terms of about 1,300 atoms, I believe. So thousands of coordinates here. Everything is, all interactions are given by the charm force field, so no harmonic Bath assumption or anything like this. We can convert this actually pretty straightforwardly and much faster now these days. This was like 4 years ago that we did this. So QCPI has turned into a very practical, I would say, approach for describing things like this, like electron transfer or extant transfer dynamics in or non-adiabatic dynamics in small systems with very complex environments. Okay, I think we're going to move on here and talk about the third class of problems, which are systems, literally large systems with a basic one-dimensional topology like this. And I have some examples here, like long organic molecules or molecular aggregates like this, or these kinds of systems here, like light harvesting systems, conducting polymers, lots of systems. Spin chains are important in quantum phase transitions and also in qubits for the coherence of qubits, lots of different kinds of effects. So this is what we're going to focus on. And I say this is a quasi-1D topology because our chains can have branches and they can have different, they can be rings, for instance, all kinds of things like this. So the let's think about a molecular aggregate, for instance, or a chain of units. I have these units that are in a single file arrangement, and these are the different molecular units here. This could be in the different molecules. And let's say I want to study energy transfer, for instance. So each of these could have 2 electronic states, or I might be interested in studying magnetic materials, and each of these molecules might have a spin here, which is a 2-state system as well, or it might have 3 states in each of these. But each of these states, if these are electronic states, for instance, is coupled to many, many molecular vibrations. So I could have 100 vibrational degrees of freedom in each molecule, for instance. So now you see that the electronic Hilbert space of this is 2 to the nth, where n is the number of units. And if I have 100 vibrational degrees of freedom per molecule, and I'm looking at finite temperature properties, I'm going to have a lot of states to account for here. If I have 3 states on average that are thermally populated, and I get this number of vibrational states and couple this to like electronic states, you see they have a vast Hilbert space if n is large. What can we do about these systems? So instead of using wave functions, again, we're going to go and look at the path integral decomposition of this. So I'm going to start with this cartoon diagram here, and I'm going to assume that these are my units here. These rectangles are my units, molecular units, and I'm going to represent the quantum paths here on this discrete time axis. So I get these are the coordinates separated by time steps for unit A, and similarly for unit B and unit C, and so on. And I'm going like this. And now all these units are coupled to each other. So I indicate those couplings with these dashed lines here. So you see that now I have turned the problem into a problem where I have this 2-dimensional lattice, where this is the aggregate unit coordinate. This indicates this dimension indicates which system, which unit I'm working with, and the other dimension indicates the time. So I have this 2-dimensional lattice, and then to evaluate the path integral for this whole thing. If I were to use a wave function, I would set up the wave function for all my units, they're all coupled together like this, and I would need to integrate to sum the lattice this way. And this is not practical because each of these units alone has a huge Hilbert space of vibrations that are thermally populated. Instead, we're going to go the other direction. So we introduced this about 3 years ago, 2.5 years ago. And what we do is we generate the quantum paths for each unit, and then we just join the quantum paths of one unit to those of the next unit. It's actually pretty straightforward, and there is a lot you can do here. You can do some more tensor decompositions and factorizations, we call them here in this case, and the whole thing becomes a lattice, like a checkerboard, like this. So we bring in the blocks one at a time. It's like building with dominoes, or building blocks like this. Bring them one at a time, and we can go just by building like this. We have linear scaling with the length of this aggregate, the number of units, linear as opposed to exponential. Okay, so some structures here, more complex structures. So also I should say the advantage that we get of the path integral, of course, is that we can also account for all the vibrations inside each of these units exactly the same way that we can account for vibrations coupled to a system in the harmonic bath picture I was describing before in QAPI. If there are harmonic vibrations and we have anharmonicity effects, we can account for those too, actually, to a larger extent in many cases. So that's the big advantage is if I have molecular vibrations here, they're normal mode vibrations, I can account for them exactly at essentially no additional cost. So we a lot of applications here we're doing. Reshmi is a grad student. She's working on Ising chains, and there are lots of interesting effects here having to do with coherent dynamics of these chains and magnetic materials and quantum phase transitions, all kinds of interesting things here. But I want to tell you about extern vibration interactions. So electron vibration coupling. All right. So we have an aggregate like this, a molecular aggregate like this, and each of the units is a molecule that has two electronic states, and we are interested in energy transfer now. So this molecule here has two states, and I can excite the molecule to the excited electronic state, and then I'm interested in watching how the energy moves throughout this aggregate. This is often described by this Frankel-exciton Hamiltonian, which is a sum of units, a sum of Hamiltonians described in different units, with couplings between nearest neighbor electronic couplings between the units. So the molecular Hamiltonian for each unit has a number of electronic states, typically 2, but could be more. And then there are all these quadratic degrees of freedom here if I'm using normal mode vibrations. This is the vibrational bath for each of these units. And we want to calculate the dynamics of everything here. So, I'm going to tell you about some calculations we have done recently on chlorophyll aggregates and also some other aggregates, and looking specifically at the extent of quantum coherence and its loss because of vibrations. So in this case, so I'm going to look at the first system I'm going to describe here, I'm going to tell you about is this, are these types of aggregates that here like this, that we find in photosynthetic bacteria. The light harvesting system of photosynthetic bacteria in plants is made of those rings that are known as light harvesting complexes, and LH2 has 2 of those rings, the B850 and the B800 ring, and I'm going to look at the B850 here, and that has 18 units in some of these bacteria. Each of these units is going to be a bacterial chlorophyll molecule, and I'm going to see what happens as I increase the length of this chain, if I increase the number of chlorophyll molecules, and I'm going to go from 2 to 5 to 9 to the full B850 ring. Okay, so let's skip something. Yes, here it is. So in that case, we are actually very fortunate. One of the issues, there have been a lot of studies on this, because there's a lot of debate about these kinds of questions here. And one of the issues is that you can do calculations and make assumptions about what the environment does, or what the normal modes, what the parameters of the normal modes are. And depending on what you put in, depending on different descriptions, you can get different results, different dynamics. So we're very fortunate here, in this case, of the case of bacterial chlorophyll, the frequencies and coupling constants of the normal mode vibrations for each chlorophyll molecule are known very, very accurately from spectroscopy, spectroscopic experiments. They have reported 50 vibrations, the parameters 50 vibrations, the Huang-Gris factors of all of them. And we take these exactly as you can see them here, the Huang-Gris factors. There's nothing else we need to input in the Hamiltonian other than a single parameter for the electronic coupling, which we took for electronic structural calculations. But because the single parameter can also vary this easily and see whether our results are robust. So what you see here is a dynamics in the bacterial chlorophyll dimer. And you see that we get, this is the population of the initially excited state, and you see large amplitude oscillations. So for reference, if I didn't have the vibrations, this would be a cosine function. It would go to 0 and back to 1 and down to 0 and back to 1. And you see that the vibrations are reducing the amplitude by about a factor of 2, roughly, in the chlorophyll dimer. And that's they mimic a dissipative effect because of that. But we still see quite a bit of coherence remaining here because we see this oscillatory structure that persists for a while. Now, when I go to a system, to an aggregate made up of 5 chlorophyll units, in the absence of vibrations, I would get this curve here. You see a recurrence at this time and continues like this. Now with vibrations, this recurrence is suppressed from about 1 to about 0.4, less than 0.4. And this is the pentamer. And if I go to a long chain that has 18 units, I think the caption is hiding this figure a little bit, but okay, here it is. What you see is now the recurrences are suppressed much more, and we get very minor oscillations here. You can see the oscillations here, a bit enhanced actually in this picture. These pictures here with color. This is the monomer number. So we're starting with in the chlorophyll ring. We're exciting the central here ring, or one central molecule, one molecule. If it was a chain, it would be the central molecule, but if it's a ring, there is no center, right? So we're exciting a molecule, and you see how the excitation spreads as a function of time, kind of away from this molecule in a wave-like nature, wave-like pattern, but it's a very small amplitude oscillation that you see here. You see it's under point, it's around 0.1, about 10% here. These are the oscillations that you see here. So the vibrations are very efficient in quenching the oscillations in the system. And why is this? That's because the longer the chain, the longer it takes to form large amplitude recurrences, because you have to travel far away and come back. It takes more and more time as you increase the length of the chain. And dissipative effects are more and more effective as time progresses. So when the recurrences occur later and later in longer units, the dissipative effect on vibrations is much more effective and quenches these oscillations. So this is in the absence of a biological environment here. This is the isolated ring in the B850 complex with very, very accurate parameters, full quantum mechanical calculations. We also have calculated coherences and all kinds of other things. And you see there is a small degree of coherence left, and the process borderline between being coherent and overdamped. And if we were to take this and place it in a biological environment, in the protein, coherence could be quenched even more, it's going to be enhanced. So we think this is kind of interesting with regard to all these studies and all the debate there is about this problem. And I'm running, really late. I'm going to tell you really quickly about another system here. And this is the electron vibration dynamics in aggregates of peryl and bismuth. These are the PBI molecules, are very much interest for energy transfer. And we have done calculations where we took molecular parameters of 28 vibrational modes from Oliver Kuhn's group in Germany, and we have 28 vibrations per monomer, and we're looking at long aggregates of 25 molecular units. That's a lot of vibrations, by the way. And we look at the dynamics in small chains, like a dimer here, and in this long chain, and you can see really some very non-trivial effects here from these vibrations. Also, I'd like to emphasize every molecule is different now, and the ability to include those different vibrations with their precise parameters is important, because this is not the same as a chlorophyll molecule. The dynamics are very, very different. So what we see is in this dimer, for instance, we can do temperature effects, and you see that there is a significant temperature effect in some of these maximum and minimum of the peaks, but other peaks have no temperature effect. And if we go to the long aggregate, you can see a bigger temperature effect at longer times. So what is going on? How can we understand this? We can actually understand this completely. We can reconcile this by studying the vibration effects one at a time or in groups. And what you see here is that the electronic populations, if I didn't have vibrations, would be here, the snapshots of electronic populations along the 25-unit aggregate, and you can see a lot of holes here and a lot of oscillatory patterns without, in the absence of vibrations, but with vibration, you can see the smearing effect vibrations, and you can see how these turn into like more blob-like structures because the energy is spreading out and is not doing this in a very oscillatory way. So what I was saying is that we can track the origin of those effects from the vibrations, and what we have done here is we analyze them by grouping the vibrations into three groups: the low frequencies, the intermediate frequencies, the high frequencies. There's nothing here in this particular molecule. This is just empty space here in vibrational frequencies. And what we see is that at very short times, it's only the high frequencies that contribute, but only true at very short times. And very soon, you get contributions from the intermediate frequencies and the low frequencies. And these are very non-trivial contributions. These are not the kinds of effects that you could really describe and imagine exactly and understand without doing a simulation. Oops, here. And we can get very accurate pictures of how electronic and vibrational effects play out together. I keep moving too fast here. Here, play out together and how they couple. This is a very detailed picture here, non-adiabatic dynamics. You can see the electronic vibrational density here. Here's the electronic, here are the two electronic coordinates, two electronic states, and this is a vibrational coordinate here of one of these coordinates, a more important mode, that's a vibronic mode. And you can see how the vibrational density changes and evolves in the two states differently. Here, two states here differently. Sorry, this was without vibrations, this is with vibrations, right? So I should say here, the left state, the excitation localized on one molecule is the right state, and the other molecule is the left state. And you can see very different patterns. You can see how complicated this neuroadiabatic evolution is, and these effects, and this is the total density. So we can do the studies very easily now, and these are numerically exact calculations. We can really understand all these neuroadiabatic effects and the origin of these effects and see what they do for our systems. So well, I'm not going to say anything about this. There is a very, very recent extension of this. Now we can extend the MPI formulation also to the to make it iterative, so we can study long times. And this is a small matrix decomposition, like the SMAP pi idea described before. We can apply this now to MPI as well, and we can go to long times this way. So I'm not going to say much more about this. So just to summarize, here there are a lot of things you can do these days with real-time path integral methods, and they provide a complementary approach in chemistry or physics or quantum mechanics. There's not going to be a universal method that solves all the problem, right? So it's really nice to have different methods that can do different problems. So if you have a small molecule or intermediate-sized molecule and you're interested at the ground state dynamics, for instance, you take a particular method, maybe wave function-based method, and every different class of systems requires different kinds of methods. So it's nice to have the complementary methods that can tackle different kinds of problems. So what I hope I have shown you is that real-time path integral methods are fantastic for condensed phase problems, especially for charge transfer, system bath Hamiltonians, and external vibration dynamics in large systems, and they allow us to do simulations that cannot really do by wave function-based methods. So I'm going to just thank my group. I think I already mentioned some of the people who do the work. Most of the work, actually, I discussed near the end, I didn't say the name, was done by Sohan Kundu, fantastic student. He has done all these calculations of external vibration dynamics and has been developing the API methodology very, very nicely. And this is a photo of Champaign-Urbana. My house is maybe about here somewhere. And I would like to just to also acknowledge the funding agencies and thank you very much for your attention, especially just before Memorial Day weekend.
Right. On behalf of everybody, thank you. Yes, thank you for sharing such an amazing body of work. And we'll get straight to the questions from the audience, since there's quite a few. The first one comes from Joel Yunju, and the question is, if the environment Hamiltonian couples to the momentum degrees of freedom of the system, for example, if we have an electromagnetic field where the vector potential couples to the momentum of a charged particle, then the influence functional also depends on such degrees of freedom. Does that cause any complications?
So thank you, great question. So for a harmonic oscillator, position, momentum are very similar variables. Whatever you can do with position, you can do with momentum as well. And it would be a very similar, we have not really worked with this, but it would be very similar influence functional. Okay, I think probably I'll just stick to this. Yes, thank you.
And I guess I'll ask the next question. Thank you very much for the wonderful talk. So the next question is from Farnas Jakib. And this person asks, is QCPI applicable in the case of coupled motions of quantum particles, such as, for example, proton coupled electron transfer?
Yes, absolutely. So it's a matter of complexity, right? So the effort grows with complexity. So if we're talking about solution dynamics, then the way to do this would be the QCPI approach, right? So that's something we have not done. Actually, we've thought about doing these kinds of things, but if it is if you want to make a harmonic bath description, then we can handle much bigger systems than that.
Thank you.
Our next question comes from Matthew Du. And the question is, how would the implementation and practicality of QAPI change if the environment gives rise to multiple memory timescales?
Yes, so actually, we have thought about this. We have a number of additional tricks that we can use here, which I did not mention. One of them is a blip decomposition applicable to strongly incoherent dynamics. Another one is a renormalization trick that I wrote a paper about several years ago. So what you can do is treat the dynamics over a very short scale exactly, and then as you go to when you have those long range interactions, like coming from low frequencies, you can essentially increase the grid, or you can basically replicate your system and like in a renormalization kind of approach and handle very long interactions this way. Yeah, that's a great question, actually. Very, very interesting. Also in SMATPI that I mentioned, there is a recent implementation, and there is an extension where we can cover very long memory without quite covering accurately all the correlations. But the calculation I showed, we can go to 200 times those of memory is based on that.
Thank you.
Okay, and the next question comes from Kai Lu, and it's a two-part question. The first part is, how does the QAPI method perform when the bath modes are anharmonic? And the second related question is the path integral method more time-consuming when the spectral density is arbitrary instead of a simple, like a Drude model?
Okay, so I'll start with the second one. So our methods don't care about the spectral density being a Drude or anything, actually, at all. So I showed you this calculation. The spectral density is just, oscillates up and down very much. So we have no dependence whatsoever on the number of Drude terms. We don't do any Drude decomposition or anything like that. We just use the spectral density as is. We need integrals of spectral density. That's all we need. And the other question was about anharmonicity. So the methods, the QAPI method and the SMATPI method, are for harmonic baths. However, we've been able forever since the 90s to include anharmonicity, diagonal anharmonicity in the vibrations. So if you have diagonal anharmonicity, we can do that very well, actually. And if you have full anharmonicity, then that's not a bath. I don't call it a bath anymore. Then I would go and do that with QCPI, which is not restricted to any kind of model bath Hamiltonian.
Thank you.
Thanks. The next question comes from James Gaynor, and the question is whether it's reasonable or productive to sum selectively over specific Q coordinates to obtain influence functionals that represent specific physical processes in a system and path that may be more interested in understanding.
Okay, so I'm not sure I am following here. I mean, we are including all the coordinates. Is the question, are you asking whether I should further decompose it or? Because
I can maybe I can maybe provide my understanding of this question, or we can ask the participant to unmute themselves. But I
can
think
ask
that
James to unmute if you'd like.
okay, yeah, that sounds good.
Be better at this by now.
Okay, can you hear me?
Yeah, good job, James.
Oh, okay. Thanks, Nancy. Yeah, my question was maybe to simplify the problem. If you have so many different coordinates in your influence functional, is it ever reasonable, or would you ever think about doing that just to like target one particular type of coordinate? Say you knew that like one solvent coordinate helped the proton coupled electron transfer dynamic or something, just as an example. That's what I was thinking.
I see. Okay. So thanks for asking this. Actually, the path integral influence functional doesn't care for how many coordinates there are. The more, the merrier. That's all I can say. We can have 50, we can have 500, we can have 10,000. Doesn't matter. All I need to do is evaluate the one-dimensional integral at the beginning of the code, right? A one-dimensional integral over 50 terms or 1,000 terms. I mean, it's done like that, right? So we don't care. So that's why we don't separate it anymore. We don't do anything else. And that's why, as I said in the last part of the talk, with MPI, we're including all the molecular vibrations there are in each unit, in each molecular unit. So in the case of bacterial chlorophyll, we had 50 vibrations given from the experiments. The experiment said there are 50 vibrations of coupled electronic states per molecule. And with Cohen-Griess factors, right, we take 50. If they had said there are 200, we would have taken 200, right? It doesn't matter at all. So at this point, we're actually limited more by availability of good electronic structure than by dynamics. So this is, I probably should have said this to all of you, okay? If anyone's interested, has interesting problems and good parameters, good Cohen-Griess factors, things like this, talk to me, because that's what we don't have in many cases, describe interesting processes. So, yeah.
Thank you. And James, do you want to unmute yourself and ask your next question related to non-secular dynamics?
Sure, yeah. We can also get to other questions, and I can ask this when in the networking session after this. I'm totally fine with that.
Yeah, you can go ahead. I think this is a really interesting question.
Oh, okay. Yeah, I guess my second part of the question is there any reason that in this path integral formalism that you use that you would have non-secular Redfield dynamics, such as like coherence to coherence transfer or coherence to population transfers, treated any differently than dynamics within the secular approximation, such as just population relaxation, for example?
I mean, in a quantitative, all the effects are in the path integral, of course, exact, right? So in a quantitative way, the results are different unless you're in a weak coupling limit still, unless you're in a weak coupling limit and don't have any of them of the assumptions of radical theory, for instance. In general, results are quantitatively quite different from what you'll get with radical theory. But all the effects are there, all the coherence, decoherence, interactions, dephasing, memory effects, everything is in the path integral. It's exact.
That's amazing. Thank you. That's cool.
Thanks. So the next question comes from Joel Junjo again, and it is related to whether there's any computational tricks to treat quantum dynamics of systems that look like aggregates, but where the number of monomers is really, really large, like in the thermodynamic limit, or would you be restricted by the scaling with numbers of monomers?
Yes. So as I said, for aggregates that have a basic one-dimensional topology, like a chain, one single file arrangement, or they could have side chains, right? But basically it's a 1D topology. We had linear scaling the number of units. We stopped at 25 in the case of PBI that I showed because you just picked a number, right? So we have linear scaling with a length. We can do any of these things. Now, if I have something different, like a 2D or 3D topology, that's a very different problem. We cannot do this right now, but who knows? Hopefully.
The next question comes from Stefan van Wildenberg, and I believe it's on the last part of your talk. The question is, in the case of L equals 5, and I believe it relates to the light harvesting complex. In the case of L equals 5, are you able to see revival of the coherence? And the question is, what would be, sorry, zoom out here. Would you see revival of the coherence, and what would be the time scale?
So here it is. Here's the L equals 5 and 60 femtoseconds. And this is significant coherence, about 0.4 population reaches 0.4 in 60 femtoseconds. And this is still a pretty small system, right? Pretty small aggregate, intermediate size. But once you go to 15, what I'm showing here is 15, this is gone.
Okay, thank you.
And then I believe we're getting towards the end of the questions now. And the next one is from Paul Siders. And the question is whether quantum computing would promise any particular advantages for path integral calculations.
All right. So I think quantum computing can solve all the problems, right? If it becomes reliable and practical. I mean, it's like a simulation, right? I mean, the molecule knows its own wave function. The molecule knows how fast the energy moves around, right? So, I mean, if quantum computing becomes a practical tool, a lot of these problems, most of these problems probably will be solved immediately, right? You won't need to do the path integral probably, I don't know. Or you could, but you would get an exponential speed up, that's the idea. So we're trying to develop all these methods while we don't have quantum computing in our hands. But yeah, great question. I don't know. Yeah, I suppose all the problems will be solved. Maybe I will retire by that time.
And we have the last question from the audience is from Argadip Koner. And this person asks, what problems would you expect if we do something like Ehrenfest dynamics on a massive number of degrees of freedom?
So Ehrenfest dynamics is known to not give the correct physically correct results. For instance, because it takes the average of it takes the average force with respect to the wave function. When you have a reaction and the wave function splits into two lobes because you have to get two different products, one going this way, one going that way, and you take the average of these, when you have two humps in the wave function, the average is the same as it would be if you had a single hump in the middle. So Ehrenfest and mean field methods of this type cannot differentiate, cannot give you this bifurcation to different products. So you might describe an electron transfer reaction where instead of getting two products, 70% covalent product and a 30% probability of ionic product, you would get perhaps a single product where half the electron is transferred. Right? I mean, that's a typical problem with Ehrenfest. So, and that's why there are methods that deviate from just applying Ehrenfest. They do surface hopping and all kinds of things to avoid this mean field, this averaging with the wave function, which leads to unphysical branching ratio.
Thank you. And that was the last question.
All right, thanks. Thanks, everyone.
Yeah, so Nancy, first of all, thank you very much. This has been wonderful, and I can see that we're running a little bit long today. But if the folks who are not students or postdocs want to head out now, and we'll give, maybe if you're willing to give maybe 10 minutes or so. I know it's running a little bit over to chat with the graduate students and postdocs. That would be super. So thank you very much, and give people
Thank you. Thanks,
chance
everyone.
to